about it gets said that we're losing people, but anyone, come in. So welcome everyone. It is my pleasure to introduce you to Mike Grudić. He's coming to us from Flatiron, but actually he's Canadian. He did his bachelor at the Memorial University of Newfoundland. Spent the summer here as a summer undergraduate at CITA, so it's great to have him back. And then you went to Caltech for your PhD. You've been at Sierra for a short postdoc, and then back at Carnegie as a Hubble Fellow. Now at Flatiron. He's a purely Barron's guy, but he's really fun to talk to. So if you still haven't signed up to chat with him, he's here tomorrow and Wednesday. So he's gonna talk about feedback early in the universe. It's all yours.
Thanks a lot, Marta. And yeah, thanks everyone for coming. Yeah, it's always great to visit. It feels like I either know or collaborate with roughly like half of you. So like a lot of the stuff I'm going to be showing today might not be so new to some of you. So especially thank you for coming anyway. But I've got some new movies that hopefully you'll enjoy. All right, so let's get into it. I want to talk about feedback. That's basically all I do. So I don't really like giving really long talks. So instead, you're going to get multiple shorter talks. We're going to break it up. So first, I'm just going to talk about star formation and feedback. What is this stuff? Why does it matter? Then I'm going to talk about my sort of main project and collaboration that I try and coordinate these days, called StarForge. It's these new star formation simulations. Then I'm going to talk about some things we've learned about the stellar initial mass function along the way, kind of delving down to smaller and smaller scales in simulations. And then I'll tell you just about some kind of cool stuff that I think we can either do with the simulations or are currently working on in the collaboration. And there's a lot of stuff there, including stuff going on in this department. So feedback, why do we need it? Well, coming from a galaxy formation perspective, there's a very simple reason. One can work out with very good confidence how many dark matter halos of different masses there should be and get a mass function that looks something like this. But of course, when we count up how many galaxies there are of different masses, we don't get this naive result that one might expect if just every galaxy got its fair share of baryons. We get something more like this. So there's a big deficiency both at the low mass end and the high mass end, and the most widely accepted and, in my opinion, plausible explanation for this is due to various feedback processes. So at the high mass end, Kunyi will not be speaking today. This is from another department. On the high mass end, it's believed that feedback from active galactic nuclei provide the engine to regulate galaxy formation. On the low mass end is the stuff we're going to be talking about today, which is stellar feedback. So stellar feedback comes in many different flavors. One of the most immediate when you have any sort of collapsing protostar or protostellar envelope is these bipolar outflows that are pretty ubiquitous in stellar nurseries. And it's been possible to image these things in absolutely beautiful resolution, looking at these molecular transitions in the IR with Webb. And what's going on there is you've got some gas that's coming in, collapsing towards the star, accreting onto the star, but not all of that gas actually makes it to the star. Some of it ends up in this collimated bipolar outflow, and that can potentially be consequential for the subsequent dynamics of star formation. In a similar vein, of course, massive stars can have very powerful stellar winds, very rapid mass loss rates, and wind velocities of thousands of kilometers per second. So when these winds encounter the ISM, they shock, they heat up, they're going to move stuff around. Similarly, massive stars also have an enormous amount of radiation. So the radiation from massive stars can do a number of things. It can heat up the gas, ionizing hydrogen and helium, producing these H2 regions that kind of expand as these overpressurized bubbles. And the radiation also gets absorbed by dust grains, and that imparts momentum, and that can act as a radiation pressure force that can, again, move a lot of gas around. And last, but certainly not least, are supernovae. So most massive stars at the end of their lifetime go off in an energetic explosion, and it is thought that these contain most of the integrated energy and stellar feedback and are very consequential for regulating star formation on the scale of entire galaxies. So people have put in various feedback prescriptions into their galaxy formation models that have both dark matter and gas in them and some prescription for feedback. And then they can see what kinds of galaxies they get out of that. And these sorts of calculations, like Illustris and Eagle would be examples. They find that they are able to obtain pretty good agreement with things like the observed mass or luminosity function of galaxies. But according to Webb, this is what the ISM in a galaxy looks like. With all this beautiful substructure, you've got clouds, filaments, you've got voids, bubbles. And in the sorts of calculations I just showed you, this is the level of resolution they're working at. So they're not explicitly treating all of these processes by which gas accumulates in clouds and galaxies and collapses into individual stars. So that kind of touches on why this problem is hard. It's the curse of dynamic range. You have this enormous range of scales from the largest scales of galaxy clusters and all the way up to large-scale structures even beyond this. And you have galaxies, you have clouds in those galaxies, star clusters, you have individual stars. And the problem is we can't really apply our usual intuition as physicists. We love to use decoupling of scales to solve problems, right? When we want to know the energy levels of the atom, we don't really need to know much about the internal structure of the nucleus because they're separated in scale and energy. Of course, in this problem, if you screw things up on the smallest scales, then feedback is just going to propagate those errors all the way back up. So you kind of need some model of this entire range to get things right. So the current state of the art, you just kind of pick a certain dynamic range that you think you want to evolve self-consistently according to your equations. And at the small end, you've got subgrid physics. And at the large end, you've got your choice of initial or boundary conditions, both of which introduce significant uncertainties. And of course, two different simulators can choose two different ranges, and then the game is to try and patch together our understanding of how this process works by kind of leapfrogging these different ranges of scales. So around the time I came into this field, there was this new generation of kind of higher resolution galaxy simulations that explicitly treated the processes in the interstellar medium and actually resolved the clouds in the interstellar medium, and also explicitly treated each different feedback mechanism in a kind of more self-consistent way. So these simulations came out. They got a lot of things right, basically for free, like Kennecott-Schmidt relation, thin disks, satellite populations, M-star and halo relation. And these were not put in by hand. They just tried to do the physics, and then this stuff came out. That was great. These models clearly have some degree of predictive power. But my job was to understand star clusters. So I want to understand why some stars form in very dense clusters, others form in more diffuse clusters, why some clusters are not very massive at all, and some star clusters are upwards of 1 million solar masses. And what is the connection between these things and the galaxies that they formed in? I want to look at our population of clusters in the Milky Way today and say something about what it looked like 13 billion years ago. That would be cool. So star clusters are kind of what I want to understand. And during most of my PhD, what I focused on was these sorts of isolated cloud simulations where we're not doing a galaxy, we're just looking at what one giant molecular cloud does, 10 to 100 parsecs in scale. And you can see that in this movie it kind of collapses and you get star formation in isolated spots, which becomes increasingly clustered over time. And eventually, once there's enough stars and enough feedback, then the cloud starts to blow apart, and that's what sets the end of star formation. So if you want to know more about this game, then you can check out the talk I gave from this very spot 6 years ago, which is on YouTube. But we're just going to kind of rush through that stuff. But the long and short of it is that these sorts of calculations obtain a lot of qualitative agreement on certain issues. For example, that star formation efficiency, the fraction of the mass that you convert into stars, tends to scale in some positive way with cloud surface density, which you can justify through various analytic arguments. And you can also see that the fraction of stars that end up in bound clusters as opposed to associations that disperse scales in a certain way with star formation efficiency. And again, we have kind of qualitative agreement between different models here. So this is good. We basically have some understanding of the mass budget that we have to make these star clusters. But what we sort of learned was that feedback can be crucial in setting the star formation efficiency, because basically that's what blows the cloud apart. Radiation is particularly important. And yeah, star formation efficiency depends on environmental conditions, such as this diagram showing the dependence on surface density. So everybody more or less agreed on that. But there's kind of an issue if you want to go from this type of setup to detailed star cluster properties. And how much you really want to believe their outputs. Because these simulations I just showed you, they don't actually really make stars. They have some rule for taking a chunk of gas and converting that into a chunk of stars without explicitly following the collapse of individual stars and the feedback from them. And these models have various parameters in them. And there have been various works where people have played around with these prescriptions and these parameters and tried to assess whether this affects the answer that we get for star cluster properties. And the answer is yes. Whether you care about just the properties of the dense interstellar medium, or the mass function of GMCs, or the mass function of star clusters, in each one of these studies, people played around with these prescriptions, all of which are a priori reasonable sounding, and got very different results. So that means that that's kind of the limit of our predictive power on the scale of star clusters. We were happy with things on the scale of galaxies, but now we're getting to star clusters like 1 parsec scales, and things seem a little uncertain again. So to summarize, these sort of 10 to 100 parsec scale molecular cloud simulations are able to investigate the effects of multiple stellar feedback mechanisms and explain some aspects of star cluster formation, agreeing on some things, but we found this sort of limit in predictive power due to uncertainties in unresolved star formation. So that's why we put together StarForge. So historically, star formation simulations were kind of relegated to two opposite regimes where there were many calculations where people were following the formation of individual stars and their accretion and their feedback, generally in very low mass systems though, order 100 to 1,000 solar masses. And then there's the stuff I worked on during my PhD thesis where you're looking at larger systems, which are the systems responsible for most star formation, on 10 to 100 parsec scales, but then you run into this issue of relying on your prescriptions, and you worry you're just getting out what you're putting in. So we wanted to put together a simulation setup where we are following the formation of individual stars in a relatively self-consistent way. We wanted to incorporate all important stellar feedback mechanisms. We wanted something that could scale up to the massive giant molecular clouds that are responsible for most star formation in our galaxy, and something that is computationally efficient enough to run all the way from start to finish of star formation. So that was the idea behind StarForge, and this was largely an effort between myself and my grad school buddy and colleague David Husseinov, with the guidance of Phil Hopkins. What we did was implement this physics framework in the Gizmo code, which essentially tries to account for all of the different processes you think might actually matter in star formation. So the backbone algorithm is the Gizmo code with its mesh-free magnetohydrodynamics algorithm, which has various nice advantages for these problems. We have a treatment of n-body dynamics using a higher order integrator which is very important if, for example, you want to predict the properties of binaries and multiples over millions of years. We track individual stars in the simulation represented as sync particles, which can both accrete gas and inject feedback into the surrounding gas particles. We incorporate all of the sort of dynamically relevant cooling and chemistry processes that occur in the cold and dense ISM, so that we're getting the thermal structure and things like the Jeans mass right. And for the first time, we incorporated all 4 of these different stellar feedback mechanisms into one simulation. So just to give you an idea of how we do this, so with the protostellar jets and outflows, we use essentially a simple subgrid model, kind of with phenomenologically motivated parameter choices, first introduced in Cunningham 2011, where a certain fraction of the mass that gets injected into the jet gets accreted by the sink, gets injected into the jet, and then we launch the jet at a certain fixed fraction of the escape speed at the protostellar surface. We launch it in these sort of collimated jets by injecting new Lagrangian resolution elements into the simulation and then following their hydrodynamic interactions. We account for radiation in 5 different bands, all of which kind of have different distinct feedback effects. So arguably the most important is hydrogen ionizing radiation, which creates these H2 regions that expand and create these bubbles in clouds. There's a photoelectric band, which is responsible for a lot of the heating that happens in the interstellar medium as well, and a lot of the chemistry. There's the near UV band, which carries actually most of the momentum present in the photons from a young star cluster. There's the optical to near IR band, which is usually the most important for determining the dust temperature and also carries significant momentum. And there's the mid to far IR band, which is treated as this sort of variable black body with a radiation temperature that can vary according to local conditions. And we solved radiation MHD equations using the M1 closure for the Eddington tensor. We treat stellar winds in a relatively simplistic prescription, but using essentially reasonable estimates of the mass loss rates of OB and Wolf-Rayet stars. We have sort of 2 different techniques for injecting the winds, because the thing is, you can't always resolve the full structure of the wind bubble. The innermost scale is the free expansion radius, inside of which the wind sweeps out its own mass. And that's not always resolvable, so we use just a sort of local injection of mass, momentum, and energy in that regime. But sometimes we can resolve the free expansion radius and the structure of the wind. And in that case, then we just directly inject mass elements into the simulation and follow those as we normally would. And supernovae, we always just directly inject the ejecta into the simulation and follow it hydrodynamically with a mass resolution of usually around 10 to the minus 3 solar masses. And it's a simple prescription, which is definitely wrong, which is just every star more massive than 8 solar masses undergoes a 10 to the 51 erg supernova at the end of its life. But we'll see that these details actually aren't so important for the kinds of regimes we've simulated so far. So just to give you an idea of what goes on in one of these simulations, this is a movie of the first simulation we fired off with this full physics setup. So we start with a 10 parsec radius cloud with 20,000 solar masses in it. It's got some initial turbulence, an initial magnetic field, and we just kind of let it go from there. And it undergoes this process of kind of turbulent collapse, where it's collapsing into a kind of network of shocks and filaments and hubs, producing these dense pockets, which go on to collapse into individual stars. And as these individual stars accrete, they start giving off feedback in the form of bipolar jets. By the way we're color coding this, so color indicates velocity dispersion, so orange is fast, purple is slow, and lightness tells you density. So you can see some of these stars are getting more massive than others, and they're sweeping out Stromgren spheres and opening up their own bubbles. And we're also getting some degree of kind of collapse and assembly of a central star cluster. But by this point, there's so much feedback around that the cloud can't really take it anymore. And it starts opening up a cavity in the center of the cloud. The collapse of the cloud starts to get reversed. And star formation is ramping down by now. And then the first supernova comes, and that kind of puts the final nail in the coffin of star formation in this cloud. But it was already ramping down, and the supernova came kind of late because the cloud is getting dispersed by the combination of winds and radiation, which are present immediately once you have massive stars. So this was kind of cool. We started from just gas, and we simulated star formation all the way from start to finish. And then you can do a lot of fun things studying the stellar population that comes out of it and how that stellar population assembles. So that's StarForge. Now I want to talk about the IMF. And the IMF is really important if you want to understand any of the things we were talking about. In star clusters, it's going to be pivotal for star cluster dynamics and evolution. The number of massive stars you have is also going to determine how much feedback you get from that star cluster, because it's basically all in the mass of stars, pretty much. So we need to solve this problem if we want to say anything about feedback and take what we've learned and apply it to other problems. So this is a compilation plot of IMF measurements. You might not be used to plotting the IMF this way, but we're plotting the IMF slope as a function of stellar mass range. So each one of these points has a horizontal range, that's the mass range it's measured in. And then your usual salpeter slope is minus 1.35 on this diagram. And yeah, each one of these points is a measurement. If you look up the plot, you can actually click on each one of these points and it'll take you to the study that it came from. But the main take home I want to emphasize here is that there's clearly a lot of regularity in the IMF. These points are not scattered all over this plane randomly. Whether it's universal is the subject of debate, but certainly there's a great amount of regularity that we would like to understand. People often talk about the peak of the IMF, so that's where the slope goes through zero, the kind of peak of the sort of log normal form, and that doesn't really vary all that much. Another thing I'd like to emphasize here is that there are a few examples of shallower high mass slopes that have been measured in various regions in recent years. So that means an excess of massive stars. And these have generally been in the most extreme regions of star formation in the local group, so 30 Doradus and the Galactic Center. So why am I saying that? Well, it'll be important later, so we'll get back to that. Okay, how do we make an IMF? Well, we can start with a simple premise, which is that the dense interstellar medium is roughly isothermal. So you can actually play around with this little data app I put together, which lets you, let me pull that up on the Zoom. Yeah, so this is called the IS emulator, and you can play around with the effects of different conditions and different physical processes on the thermal structure of the interstellar medium. So we're plotting temperature as a function of density. The key thing here is that there's this fairly large range of density. Once you get to these high enough densities, it basically levels off. It's roughly isothermal. So that's nice because it's a simple model that we can try and solve and get an IMF out of that. We're going to keep it there. It is. Right, now, Hoyle presciently kind of had an idea of what might happen if you have a self-gravitating isothermal medium. And basically, it's that if you form something dense, it's not necessarily going to have a tendency to disperse like a normal structure would in turbulence, but it might become bound and collapse more, and then fragment more once it reaches that higher density, because the gene's mass just keeps getting smaller and smaller and smaller. And Hoyle's prophecy was borne out in simulations, it turns out. So if you assume just isothermal gas plus gravity, and those are the only things that work, and you solve that system, you don't really get an answer for the IMF, actually. Every time you vary your numerical resolution, you just end up fragmenting into smaller and smaller things. So there's no scale there where you get a stellar mass of. And all of these different studies have found this. Maybe someone in this room knows how to get an answer out of this model, but no one has succeeded so far. Turns out adding magnetic fields does change things a bit. So this was a study where we surveyed parameter space for isothermal, 10 Kelvin, MHD, and gravity, and we looked at what IMF came out of that, and it looked very different. It's this more top-heavy kind of thing, but we were still not able to actually converge on the IMF. We kept turning up the resolution and getting smaller and smaller stars at the low mass end. And also the thing that we got just didn't look very much like the actual stellar initial mass function. So part of the story of what I think was missing in those isothermal studies is the opacity limit. This is not a new idea. Basically, the gas can't collapse indefinitely at an isothermal temperature. It's going to reach a point where the trapping of the cooling radiation by dust opacity becomes important, and the temperature is going to start rising basically quasi-adiabatically. And when that happens, the Jeans mass, which was initially dropping, will start rising. So you end up with this sort of minimum Jeans mass in this process, which we worked out in this recent short paper in a little bit more detail than before. It depends on both your dust opacity, which kind of corresponds to metallicity, and also the ambient radiation field. But you end up with something on the order of a few Jupiter masses to maybe 1% of the solar mass in typical conditions in the solar neighborhood. Does this work? Does this get you an IMF? Well, these works modeled the opacity limit using a barotropic equation of state in their simulations, and they found that yes, when they put this in, they get something that looks more or less like these various standard IMFs.
Question. So how well is thermal pressure supported in your simulations? I can find it. There's a small scale regime where the thermal pressure dominates over the kinetic pressure.
Yes, that is called the sonic scale.
Yes.
So generically in turbulence, you have this scaling in the power spectrum where larger scale eddies have larger velocity dispersion. Then once you get down to the speed of sound with that, you get this kind of transition in the properties of the flow. That's the sonic scale, and that probably determines the properties of the individual cores that collapse into stars. So it is quite relevant.
You are talking about building supporting cores.
Yeah, once you get down to the things that seed individual stars. Yeah.
And what about the magnetic pressure support at this transition scale? How well developed important is that?
So its relative importance is actually kind of scale independent. It turns out, in the sense that everybody ends up with this scaling where the magnetic field scales as the 1/2 power of the density, which gives you a constant Alfvén speed. In other words, the magnetic pressure is never really all that different from the thermal pressure in the collapse, and many simulations find this. Yeah. But yeah, so these folks got nice looking IMFs just with the opacity limit. I wanted to see if this worked in my Gizmo setup, so I fired it off with a similar approach where I ran with various equations of state with different temperatures and opacity limits, and I found that, yeah, I could get something that looked a lot like the observed IMF shown in pink there for the right parameters. But this was for a very dense clump. Much more massive and dense than any system that's actually forming stars in the solar neighborhood. And those other studies also considered only that regime of parameter space. But when we go to more like solar neighborhood conditions, we get this really flat and kind of top-heavy thing that doesn't look a lot like a real IMF. I did find that the low mass cutoff that you get here is definitely affected by the opacity limit. So the opacity limit will give you that, but we still need to do more to regulate the high mass end in certain regimes. So then we fired off all of these sort of more complete simulations with all these extra physics I've been talking about. And the story goes as follows. So this was the picture with just isothermal gas and MHD and gravity, nothing else. Far too shallow, top heavy. Doing a more realistic job of the cooling and chemistry and thermal structure of the ISM didn't really change that. Turns out isothermal is not a terrible approximation. Introducing protostellar jets and outflows actually did make a big difference both in the shape of the IMF and the location of this kind of turnover to the high mass asymptotic scale 3 part. And then introducing all of the other feedback physics, so winds, radiation, and supernovae in the full physics package got us a much more reasonable looking high mass cutoff in the IMF, whereas with just jet feedback alone, that couldn't actually stop the accretion of very high mass stars. It just kind of punched a hole in the cloud, but gas could still get in. So the picture that sort of emerged was that protostellar jets play some key role in regulating the location of the IMF turnover from the saltpeter part and its general shape. As we saw, the opacity limit sets the low mass cutoff, and the high mass cutoff is clearly strongly affected by the effects of radiation and winds from massive stars. And that's kind of self-evident, right? Because that's what's blowing the cloud apart and cutting off the gas supply to grow these massive stars. So I got interested in kind of the nature of this high mass cutoff.
Sorry.
Oh, yes.
Sorry, lots of information is flowing very quickly, so hard to digest all. The jets, which mass range is dominating the jet energy, collective jet energy budget?
It's the massive stars. Most of the energy is in from the massive stars.
Is it just basically where the PMs according to are, and so that's common? I mean, all that with the mass function, we find that high mass end minus.
I don't think so, right? Because you have a lot of low mass stars per high mass star, and the potential well is not that much deeper in the massive stars than the low mass stars.
Yeah, it's not like a global regulation effect where the jets from the massive stars really does much to the growth of the low mass stars. Like each low mass star is regulating its own growth from its jet. So you need to consider it on that scale rather than just the global energetics. But yeah, I got interested in this high mass cutoff. So I ran this experiment where instead of running one big star cluster, I ran 100 low mass star clusters, stacked their IMF, and then examined the statistics of this high mass cutoff. And my initial question was whether the high mass part of the IMF is just sampling a pure power law and the maximum mass you get is just from that, or whether there is some actual kind of Schechter-like cutoff in the mass function. And that is what I found here. So in other words, the upper cutoff, or the maximum mass that you get in a star cluster, is not just the size of sample effect in these simulations. There's a physical cutoff scale. It's also set by feedback physics, as we mentioned. For comparison, this is one cloud without feedback, made a 200 solar mass star, not present in any of the feedback clouds. And it also depends upon cloud properties. So for example, this one high mass cloud made stars more massive than these 100 low mass clouds, even though they have more stars overall. So that's interesting. And really, if you think about it, it's not that crazy. You can imagine a sort of toy model where you have a gas clump of a certain mass and a certain surface density, and you ask how much feedback do you need to blow that thing apart within one free fall time. If you treat it in the momentum feedback limit, then you find that you need a momentum injection rate that scales as the product of the mass and the surface density of the cloud. And that could be either from radiation pressure or from radiatively efficient winds. If you consider it in an energy feedback regime, like a radiatively inefficient wind, Then again, you need a wind luminosity that scales as a positive power of mass and surface density, and for photoionization, a similar sort of story. So denser and more massive clouds tolerate more massive stars without being disrupted. That doesn't get you all the way to the IMF, but it's kind of the physical principle at work here. Another interesting thing happens as a function of metallicity, actually. So very massive stars are basically pinned at the Eddington limit, set by the free electron opacity, the Thomson opacity. So you get this mass-luminosity relation. But the flow that they accrete from, the opacity is dominated by dust. This dust opacity scales as a function of the sort of dust-weighted metallicity of the flow. And if you calculate the ratio of the radiative force to gravity in this scenario, when you're pinned at this Eddington limit, then you get just this pure function of the metallicity. So what this tells us is that if we plug in just solar metallicity, then radiation pressure on these dust grains is super important, and the gas has to do fancy things to actually get to the star. But once you go to lower metallicities, then this effective radiation pressure on dusty neutral gas doesn't work anymore. You just don't have enough opacity. So that could make it potentially easier to grow a more massive star in less dusty environments. So one way we can test this out is by running at low metallicity and high density. I fired off this run basically kind of interested in sorts of high redshift conditions people have been looking at with JWST. So this is 100 times denser than the cloud I showed you before, and it has a metallicity of 1% solar abundances. And I got a very striking result from this simulation. I got a maximum stellar mass of about 1,800 solar masses, plus 3 other stars, roughly 1,000 solar masses, in a quadruple system formed here at the center of the star cluster. And eventually star formation in this system is disrupted by a powerful 100 kilometer per second stellar wind-driven outflow. But the IMF we get out of this is quite unusual. It is top-heavy. It's both offset with respect to the standard IMF, so they would be considered bottom light. And it's kind of shallow. But then we get these guys up here. So these roughly 1,000 solar mass stars. And these actually have half of the mass of the whole cluster. So if you ask what the UV light to mass ratio of this cluster is, it's about 10 times more than a standard star cluster IMF. So I have colleagues who think about things like the UV luminosity function, nitrogen enrichment, potential supermassive black hole seeds when these massive stars die. I haven't worked along those problems, but basically these very massive stars in the right environments might solve certain problems. That remains to be seen. I got interested in how the gas actually gets to these massive stars. So this is all of the gas that ends up in these 4 very massive stars. And it just kind of extends throughout the whole cloud, like this is the cloud radius here. So this is the gas that ended up in Paul, the most massive one. This is the gas that ended up in John. This is what ended up in George, and this is the gas that fed Ringo. So you can see that there's a large overlap between the gas reservoirs that the stars actually feed from. So it's not a picture of individual fragmentation and then everybody just feeds from their own core. We can look at a movie of how these stars get their gas, and they actually all form kind of separately, but then eventually they pair up with each other. So they end up in a hierarchical quadruple system. So first the 2 pairs pair up, and then those pairs pair up. And they all end up kind of accreting from a similar looking flow by the end, because it's all just coming from throughout the cloud into this kind of very messy system that sometimes has disk-like phases, sometimes it's filamentary. It's a very messy kind of flow.
Question.
Yeah.
So, how long do these stars continue to accrete after they reach the main sequence, since they're massive stars?
Yeah, great question. These things, they according to our protostellar evolution model, they relax to the main sequence when there are around 1 or 200 solar masses. So that's when they hit the main sequence, and then they just keep on accreting along the main sequence thereafter until they get to 1,000.
I ask because you have this, one star, you can imagine maybe there's some stable accretion flow and it's self-shielding from the intense IR of the star. But when it's all dynamically active and swirling around, it's harder to the gas to avoid being, blown away, by the.
Well, remember, this is very dust poor, so the radiation pressure actually can't do all that much to the flow.
And the heating of the gas by the UV is not significant, or the oxidation is not significant.
So densities are very high, so the kind of stronger radii tend to be quite small.
So it's just recombining like that.
Yeah.
Whereas,
So we can look at the.
but what does shut it off though in the end, in this specific case? Mass accretion.
Eventually, the stellar winds that are getting injected from these stars is strong enough to just blow everything apart.
Kinetic pressure.
Are you out of gas reservoir mostly by that point? I mean, have you mostly accreted what was there and then you're just blowing away the last remnants?
The final star formation efficiency is about 50%, so there's still gas there. But you get this bubble on small scales that just runs away. Sorry, you had a question?
Yeah, just asking, are these over luminosity in the sense of, not in the sense, are the radiation pressure on electrons already?
So that they're on essentially a standard kind of main sequence stellar mass luminosity relation, which is basically, it asymptotes to the Eddington limited relation where the luminosity scale is proportional to the mass.
Exactly at the end. So they can just accrete.
Yeah. So if we plot the accretion rate as a function of mass, we actually see a lot of regularity here, and all of these kind of do a similar sort of thing. We can take out the dominant scaling in this relation, and we find that basically an m to the 2/3 power kind of compensates for this scaling. That was kind of interesting because this was actually predicted 23 years ago by Ian Bono, considering a scenario where massive stars accrete from a common infalling reservoir, and the capture radius for that accretion is set by the size of their Roche lobe. So that seems certainly qualitatively consistent with what's going on in the simulations. So I think we more or less understand that. So we get these very massive stars at low metallicity due to runaway accretion, which is kind of interesting because conventionally when people talk about top-heavy IMFs at low metallicity, they think low metallicity, less cooling, larger Jeans mass, but it's not a fragmentation effect, it's an accretion effect. We can also break down the effect of different processes on the growth of the massive stars. So this is the maximum mass.
Could I just follow up from a distance on these questions? So obviously the issue of the wind from the very massive stars, which is an issue of great interest to me, that's very tricky to get right. And
Yeah.
You're only really at the beginning of trying to model down at that level, I think. The intriguing thing I'm hearing, though, is that, and this does not surprise me, that the objects in this case came in a quadruple. And I guess that means that and I think this is what you were alluding to, that the flow is an asymmetric accretion flow rather than a spherically symmetric flow. Is that how you envisage this, or have visualized it?
And I think that's quite natural if you have a sort of turbulent initial condition. But yeah, it's not trivial that it wouldn't just be dominated by a single star, for example. So that is interesting.
Well, I mean, what that means is that you can get away from some of the issues associated with vigorous winds because it's asymmetric. And so it's
Yeah.
interesting, but you know, obviously there's so much to explore here, and it's great that you've got the res to do it.
Yeah, but as you highlighted, and I agree, the wind prescription we put into these things, like, we're basically guessing at this point. We're extrapolating existing models far beyond the point where they were intended, because there just hasn't been a lot of modeling of winds from stars of this mass. So that's the big uncertainty here. But yeah, breaking down what the different feedback physics do to the maximum stellar mass. So starting at solar metallicity, we found that at solar metallicity, we got a very reasonable maximum stellar mass, about 150 or so. We switched off winds in that setup. That didn't really change anything, but then we tripled the strength of winds. That's the green plot. And that did have a noticeable effect. So winds are kind of marginally important for setting this maximum mass at solar metallicity. We switched off infrared radiation pressure, and that also greatly increased the mass. So that's also playing a role, as we argued it should. And then, of course, when we went to 1% solar metallicity, neither of these effects are nearly as strong, so you just throw this really, really massive star. So just to leave you with my cartoon picture of what determines the IMF. At the low mass end, you've got these dust radiative processes setting the kind of minimum Jeans mass. You've got this turnover point, which is determined by turbulent fragmentation and affected by protostellar outflows. You've got this high mass slope, which could in principle come from either, again, turbulent fragmentation or accretion. It seems like it's more like accretion in our simulations. And you've got this high mass cutoff, which is determined by radiation and or winds from massive stars. And a lot of, again, this is also out of date. This review is out now in Grudić in 2024. Sorry about that. So, all right. In the last part, I'll just tell you about some other things that we've been doing with these sorts of simulations. And one of the nice things you can do when you have a setup that has all of the basic stuff more or less right is then you can add other stuff, other complications and epicycles, and do some physics. For example, now Dr. Margot Fitzaxon at UT Austin, she got her doctorate last week. She actually performed the first numerical 3D GMC simulations with on-the-fly cosmic ray transport. So directly simulating the way that cosmic rays come from outside of the cloud and penetrate into the cloud. Nina Filipova, another graduate student at UT Austin, has been taking our setup and pushing it to 100 times finer mass resolution, to the point where she is resolving these protostellar disks and investigating the importance of non-ideal MHD terms in the disk properties. Nadine Solomon, PhD candidate at Caltech, has been investigating the effect of dust dynamics in the context of star formation, because dust grains don't exactly go where the gas goes. They are aerodynamically coupled. And what that means is that large grains can actually concentrate in certain regions and be depleted in other regions. And this can do various interesting things for stellar abundances and for stellar feedback. You can also do synthetic observations with these simulations. This is an example of a work by Sam Millstone, who was at the time an undergraduate, who mocked up these sort of Herschel dust mapping observations and the correlation between the gas surface density and the surface density of young stellar objects. And we've actually got a follow-up study with a student I worked with at Carnegie this past summer. You can also do cool things with synthetic observations and machine learning. You should all talk to Duo Zhu, who just got here and specializes in this. What we did was make dust emission maps from the simulations, and then Duo trained a model so that given that dust emission, you can back out the radiation field within the molecular cloud. And there are lots of different things you can do with this sort of approach. It's very powerful. You can use these simulations as realistic initial conditions for n-body simulations. So my colleague Juan Farias at UT Austin plugged Starforge outputs at the end of the simulation into his specialized n-body code to evolve them for a longer period in the galactic environment. And I'm really interested in bridging gaps in scale. And one example of how we've done this is these recent studies led by Phil Hopkins, where we started with a cosmological galaxy simulation model, and we applied a refinement routine around the black hole in the galaxy and refined deeper and deeper down to the inner accretion disk. We've actually managed to get this down to the ISCO radius, where we have to start thinking about GR effects, which is fun. But of course, you can't just, it's not just the AGN that you can do this for. You can, in principle, do this for a giant molecular cloud, which is the project of Shivan Kular here. We should talk to him about that. So we can take a galaxy simulation and then zoom in on a single molecular cloud, and then sort of get around this ambiguity in our initial conditions by just taking it straight from a live galaxy model, which is very cool. I would also like to kind of come back to this issue of star formation prescription. So one thing I'm thinking about good ways to do is not have to do StarForge. I don't want to have to do a StarForge simulation if I don't have to. I'd love to scale this up to a whole galaxy. But if I want to do that, then, given a gas cell in my galaxy simulation and all these pieces of information about it, I need to figure out some rule to populate stellar mass and phase space in a physically informed way. I think that it's possible to directly validate existing prescriptions for doing this and also calibrating new ones to the simulations. So that's an exciting prospect that hopefully will allow us to take what we've learned in these high resolution runs and apply it to larger systems. Let's get that. So to summarize, pretty much all of the baryonic objects in our universe are sculpted by feedback in some form, whether you're talking about galaxies, star clusters, or individual stars. And I think we're really just scratching the surface of how that works, because you have to go all the way down this rabbit hole of the dynamic range in the problem to individual stars, and then take what you've learned there and propagate it back up. So it's an exciting time. We've put together StarForge, which provides this nice numerical laboratory to study all of these different feedback processes acting in concert. And we've been able to disentangle the physics of the initial stellar mass function and resolve ambiguities in star formation. So there's a lot of fun stuff you can do with this. I've talked about just a few, but talk to me later if you're interested. From the scales of planets to galaxies, and also just having a nice realistic model that can help us interpret observations. So with that, I'll take any remaining questions. Thank you.
Thanks for the great talk. There's already been some questions. Are there any more? Or online? Just unmute yourself and jump up.
I'm still curious about the Eddington luminosity on the star. If such a massive star, 1,000 solar masses, is it positionally unstable? Is that able to restore any kind of accretion, for example?
That's a great question. That is not implemented in our subgrid protostellar evolution model. I've looked for models that try to treat this regime, but nobody even really thought about the kinds of accretion flows we've been finding, or the sorts of stellar mass ranges that I could find. But I think that's one potential thing. If anything's going to stop this from happening, then it could be pulsational instability. These things also might bang into each other. They might be very large and have a decent cross section for stellar collisions, and that would inject a lot of mass into the surroundings. And potentially get that wind bubble started, maybe. I don't know. There's a lot of processes that could affect the way this plays out.
So we should take 1,000 solar masses with a grain of salt for the moment.
Yeah, I think you should. I hope I've convincingly argued that some of the basic physical processes that normally regulate massive star formation are less powerful in low metallicity environments. So certainly, the trend of more massive stars in low metallicity environments, I think that's fairly well understood and credible. But yeah, you can take my particular masses with a grain of salt for now, for sure. Yeah.
Could you comment a little bit more on, sorry,
Go ahead.
could you comment more on the stellar wind models that you were talking about there, why they're not, like you said, they're not, perfect or whatever. So what is wrong with them in particular?
I mean, my main concern is just the sheer extrapolation. Because again, people don't usually think about these ranges of stellar masses. Basically what I've done is, like, I started getting these very massive stars, and then I was like, no, I don't want to deal with this. So let me try and kill this result with the most aggressive wind prescription I could find in the literature. And I put that in, and then it still happened. I mean, this is an ongoing investigation just totally independent of star formation, where there have been these historical discrepancies between the predictions of standard, like line-driven stellar wind models and a plethora of observations, I would say, like gravitational wave people definitely talk about this quite a lot. Massive stellar mass loss in general, like pretty much whatever you want to do in astrophysics, it's something we need to worry about. But I know there has been a lot of nice progress in recent years.
So in the long-standing expectations that massive star clusters can undergo runaway collisions and form really massive stars or intermediate mass black holes. I mean, have you ever explored that?
Yeah, so that is not implemented in our model. The challenge, and the thing I very definitely neglected to mention, is that our N-body integration uses softening on a scale of about 20 AU. So that's larger than a massive star, unless it's really, really, really loaded. So we can't follow the collisions explicitly, but actually we may be able to in the next version of StarForge, because we're using this new integrator that may make it possible to just integrate the unsoftened equations of motion. And you could even just be kind of cheeky about it and just say if they come within a certain cross section, they're likely to merge.
Have you seen their collisions?
I definitely think if we were to switch this on, we would see some, especially in these really, really dense systems I've shown you. In a typical Milky Way GMC, I don't think the star clusters necessarily get dense enough for this to matter. But certainly there should be parameter space where this does matter. And for these very massive stars I showed you, like clearly they're very close to each other. Depending on how you model their evolution, they could be bloated and bigger than we model them. So yeah, they might bang into each other. But I guess I'd be surprised if in the end, coalescence was sort of a key ingredient in the IMF in typical conditions, I guess.
Somehow I couldn't put my hand up here, but from a distance, I'm extremely interested in the particle splitting and how far it can go. I've heard that Phil Hopkins describes it more as an art form than a science, because what you're doing is taking information packets and splitting them up. Of course, this was done whenever one was creating stars, etc. But the technique that is used now, how is it being checked, and how far down do you actually think you can go before the fact that you aren't putting in higher resolution fluctuations is going to play a huge role?
Yeah, that's a great question, and you're right, that is kind of early days for this technique. So this, for those not familiar with Gizmo, the hydro solver that it uses is very different from SPH. It's very different from Eulerian grid codes. So we're kind of flying on instruments here in terms of applying these sorts of refinement techniques. And honestly, I think that a lot more work could be done along the lines of what you're suggesting. So in the studies we've done so far, like Phil's fortune fire stuff, Phil's technique was basically to let the disk whirl around a few times, a few orbits, before applying the next level of refinement, so that the noise introduced by the last level of refinement sort of gets washed out, and you're left with something more physical. I think with the setup that Siobhan and I are trying to get working, that's less straightforward, and you may need to worry more about characterizing and mitigating the numerical noise that arises when you do this. So I think that would actually be a really productive investigation for someone to do. I'd love to get around to it at some point, but only so many hours in a day.
Okay, so before our next question, we're past the hour, so if you don't want to continue here, you're free to go. But Peter had a question.
Hi. Hi, thanks very much for your talk. Going back to the earlier part of the talk, kind of a summary statement. We were having a discussion in the coffee room within the last week or two about what the consensus is on where most stars in the Milky Way are born, what mass of GMCs. I remember, historically, the discussion was that they came from the very highest mass clouds, but then there was some dispute of that. What's your summary of that?
So my read of this kind of comes from measurements of either the CO luminosity function of clouds, or the H alpha luminosity function, or just general luminosity function of H2 regions, and they tend to be kind of shallow, such that the shape of the luminosity function is sort of concentrated towards the largest objects. I think the one caveat there is that I don't really know what a cloud is, and I don't think anybody really does. So I think we should be careful when we interpret cloud mass or CO luminosity functions. But at least, yeah, that's been my general impression, though, is these things tend to come out kind of top heavy.
As a follow-up, the sun is presently in a local bubble, not where it was born. And around us, we see a lot of low mass star forming regions, which interestingly, you said have a high end cutoff, not just from statistics. I think you said it was Schechter-like.
Yeah.
But anyway, that material has been gathered up in the bubble from the massive stars that have produced it. And so a more massive region, if you add up all of the mass. Can you learn from your types of simulation anything about things like the local bubble and whether they're have a chimney or not escaping out of the disk, or is that just too fine a detail for you to work on?
Well, I mean, there are simulation setups that people work on where instead of simulating a single isolated cloud, they simulate something more like just a solar neighborhood. They simulate like a periodic 1 kpc patch of galaxy. I think those would be an appropriate tool to investigate things like analogs to the local bubble. And I think my impression is like these simulations do form local bubble-like systems pretty spontaneously. And then, of course, if you wanted to know more about the high-resolution star formation, then you potentially refine on one of these swept-up clouds. But the models we've run so far don't have that larger context of the galactic gas cycle, where you could say something about a local bubble. It's just kind of an isolated cloud that blows apart.
Thank you.
So unless there are any other questions online, I think the in-person ones can be moved upstairs. In the lounge, there should be coffee and sweets, so just feel free to go upstairs. And let's thank actually Mike.